In this video, we're going to look at how statistics calculated from samples vary from sample to sample, and how this variability is captured in a sampling distribution, and try to understand why this sampling distribution is the basis for most of statistical inference. Two important terms we try to understand are the sampling distribution and the standard error. So we know about the aim of statistical inference, trying to understand a population parameter, something true, but something that's unknown. So that's why we're going to try and estimate it. And we try to do that from a sample taken from that population. And we know that we use statistics calculated from a sample as a point estimate of this parameter we're trying to understand. We understand that this statistic from our sample is our best guess at that parameter. And we call this process estimation, estimating the value of a parameter. But it's just a guess from a single sample. How good is our guess? How certain can we be? What is the uncertainty in our estimate, our guess? We have some idea that it's close to our true parameter, but we do not know how close. We can try to quantify this closeness through something called the sampling distribution of the point estimate. That's different from the sample distribution. It's called sampling because it's the distribution from repeated sampling. So imagine that we repeat the study or experiment again using the same sampling process. We're likely to get another different value for our sample statistic or our point estimate. Let's say we repeat it and repeat it and repeat it and repeat it and repeat it using the sampling process, recording the value of the statistic or our point estimate each time, and we repeat it and repeat it an enormous number of times until eventually a distribution appears that does not seem to change much when you keep adding another sample. That's all very theoretical, but that is what's called our sampling distribution of the point estimate. So the basic idea is that our point estimates are prone to sampling variation. Our estimates can change from sample to sample. They could have come out differently if we did the study again. This sampling variation is captured by the sampling distribution of the point estimate. It's the distribution from repeat sampling. The name tells you exactly what it is. And we wish to understand this variation so we can understand the uncertainty of our estimate of the population parameter, or how little our particular sample can tell us about our population. How far away could we be from the true value? It is really about quantifying the uncertainty. That's useful because it helps prevent us from making fools of ourselves, making proclamations about a population parameter that is just due to sampling variation. So let's look at an example to see what a sampling distribution looks like and what it can tell us. This is best done by considering a finite population where we have all the data, and so we know the true population parameter we're interested in estimating. This virtually never occurs, but we're just using it as a proof of principle. So in this example, we want to know the mean diastolic blood pressure in a population of 2,000 airline pilots, and we have data from the entire population. So we know the true value of the population parameter we're trying to estimate. And this is what the distribution of blood pressure in the population looks like. The true population mean is 78.2 millimeters of mercury, depicted by the Greek letter mu, our population parameter. And that's what we're going to try and estimate from taking samples. Standard deviation is 9.4 millimeters of mercury. So let's say we take a random sample of 10 pilots. Here's the data. We then calculate our point estimate, the sample mean. Is this close to our true population mean? We can see that it's different, but it's quite close. And the difference is due to random sampling variation. So if we keep taking independent random samples of size 10, extract that sample mean and keep doing it and doing it and plotting their distribution, we can see what this sampling variation or random error due to sampling variation looks like in our study. The distribution of these sample means or point estimates gives us their sampling distribution. This is what the sampling distribution looks like after 100 samples. If we were to take even more samples, then the sampling distribution would take on its true shape. So the spread of the sampling distributions represents the sampling variation or random error. It tells us how the sample mean or the point estimate will vary about the true population value. So it gives us an idea of the uncertainty in our point estimate. This uncertainty is captured by the standard deviation of the sampling distribution, which we call the standard error. This tells us how far on average each estimate is away from the true population value. So the standard error is a measure of the typical error of the point estimate, or the precision of the point estimate. The standard error is not to be confused with the standard deviation. They're different. The standard deviation is a measure of variability of the individual values, while the standard error is a measure of the variability of the point estimates. And we can see that by overlaying the two distributions. So the red bars are from the sampling distribution of the point estimates, and the background grey bluey bars are from the distribution of the individual values. And you can see that the variation of the point estimates is much lower than the variation of the individual values. However, in one aspect they're similar. The mean of the sample means, or of the sample distribution, is approximately equal to the true population mean. So if we took more and more samples until we had the true population distribution, the mean of the sampling distribution would equal the population mean exactly. This makes sense because if they were true random samples, then we would expect our estimates from repeated samples to fall around the underlying true population value. But what if we took bigger samples, a size 40 say, instead of size 10? Well, then our sample distribution would be even narrower, because with a bigger sample, each sample would be expected to be closer to the true mean, and therefore our sampling distribution would show less variation. And here's a plot of the pilot data to illustrate that. So this is called a running mean, and it's a sequence of calculated means from some randomly sorted data where each mean uses one more observation in its calculation than the mean directly before it. So the second mean is the average of the first two observations. The third mean is the average of the first three observations. And you can see that the sample mean is much more likely to be closer to the true population value as more data are used. You can also see that the mean tends to jump around less as the sample size gets bigger and bigger, and that reflects the sampling variation getting smaller and smaller with bigger sample sizes. So a few extra extreme observations are going to be balanced out by a bigger sample than a smaller sample. And this figure really shows why bigger samples are better than smaller samples. Their sampling distributions show less variation, and on average they're more likely to be closer to the true value. So that's a lot to get your head around on a first go. So let's recap the key concepts that have come from that example, and you might want to pause the video to digest this. Okay, so moving on. How do these sampling distributions help us in practice? Well, all statistics have a sampling distribution, and it is through these distributions that we are able to relate how close a statistic is to its corresponding population parameter that we're interested in. So hopefully you can recognize that the standard error of the sampling distribution is useful because it can be used to tell us how much potential error could be caught up in our estimate of the population parameter. In the example we showed where we were interested in the population mean, it can be shown that the standard error is equal to the population standard deviation, often abbreviated sigma, divided by the square root of the sample size. So the n in the denominator reflects what we saw before, that the larger the sample size, the n, then the smaller the standard error, the better the estimate. The square root of the n means that the standard error will reduce by a lot as the sample size increases in smaller samples, but then will reduce less and less as the sample size gets bigger and bigger. And that sort of makes sense, as when you have a big sample size, increasing it by a little does not add that much more new information. That all sounds very good in theory, but, we often only ever have one sample from which to estimate the population parameter. So how do we know what the sampling distribution looks like based on only one sample? And how do we calculate the standard error of our point estimate? Specifically, in the equation here, we do not know what the population standard deviation is. But it just so happens that as long as the sample size is not too small, the sample standard deviation is a pretty good estimate of the population standard deviation. And so we use that instead. That's a good result because it shows that based on a single sample, we can get an estimate of the population parameter. And we can also get an estimate of the precision of our estimate for many of the statistics and point estimates that you'll come across. So I've talked about this topic in a way that I hope will give you an intuitive sense of sampling variation and its role in inference. But we may have moved a little out of the logical sequence of things, so let's link it all together and summarise the concepts that we've just covered. So really the key messages are that all statistics, those being point estimates of the population parameters, all statistics have a sampling distribution. The sampling distribution describes the variability of the point estimate around the true population parameter from sample to sample. The standard deviation of the sampling distribution, or the standard error, is a measure of the uncertainty, or the precision in an inverse sense, because a lower standard error means more precision. So it's a measure of the precision or uncertainty of the point estimate. It's thus of prime importance for statistical inference. However, we often only have one sample or only very few samples, and so do not observe the sampling distribution of a point estimate and cannot calculate the standard error. But for many point estimates, we can estimate the standard error using the observed data from only one sample, as we saw in our example with the sample mean. So why is all this useful? Well, the standard error, or the standard deviation of the sampling distribution, is central to most of the confidence intervals and hypothesis tests you'll come across, and so underpins most of the statistical analysis involving inference that you'll read about. And you'll see it many times, so it's helpful to have some understanding of it. Lastly, here's a list of the terms that have been introduced.